Example 1, determine whether the series to sum from n equals 1 to infinity of 5 over 2 n squared plus 4n plus 3 converges or diverges. Solution: for large n, the dominant term in the denominator is 2n squared. So we compare a given series with the series, the sum of 5 over open 2n squared. Observe that 5 over 2n squared plus 4n plus 3 is less than 5 over 2n squared, because the left side has a bigger denominator. In the notation of the comparison test, a sub n is the left side and b sub n is the right side. We know that the sum from n equals 1 to infinity of 5 over 2n squared equals 5 over 2. The sum from n equals 1 to infinity of 1 over n squared is convergent because it's a constant times a p series with p equals 2 greater than 1. Therefore, the sum from n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 is convergent by part I of the comparison test. Note 1. Although the condition a sub n is less than or equal to b sub n, or a sub n is greater than or equal to b sub n in the comparison test is given for all n, we need verify only that it holds for n is greater than or equal to big N, where big N is some fixed integer, because the convergence of a series is not affected by a finite number of terms. This is illustrated in the next example. Example 2. Test the series, the sum from k equals 1 to infinity of the natural log of k over k for convergence or divergence. Solution: we use the integral test to test this series in example 11.3.4, but we can also test it by comparing it with the harmonic series. Observe that the natural log of k is greater than 1 for k greater than or equal to 3, and so the natural log of k is greater than, the natural log of k over k is greater than 1 over k, where k is greater than or equal to 3. We know that the sum of 1 over k is divergent p series with p equals 1. Thus, the given series is divergent by the comparison test. Note 2. The terms of the series being tested must be smaller than those of a convergent series or larger than those of a divergent series. If the terms are larger than the terms of a convergent series or smaller than those of a divergent series, then the comparison test doesn't apply. Consider, for instance, a series the sum from n equals 1 to infinity of 1 over 2 to the n power minus 1. The inequality 1 over 2 to the power n minus 1 is greater than 1 over 2 to the power n. Is useless as far as the comparison test is concerned, because the sum of b sub n equals the sum of 1/2 to the power n is convergent, and a sub n is greater than b sub n. Nonetheless, we have the feeling that the sum of 1 over open 2 to the power n minus 1 closed ought to be convergent, because it is very similar to the convergent geometric series, the sum from the sum of 1/2 to the power n. In such cases, the following test can be used. Sidebar exercises 40 and 41 deal with the cases c equals 0 and c equals infinity. The limit comparison test. Suppose that the sum of a sub n and the sum of b sub n are series with positive terms. If the limit as n approaches infinity of a sub n over b sub n equals c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. Proof. Let m and big M be positive numbers such that m is less than c and c is less than big M. Because a sub n over b sub n is close to c for large n, there is an integer big N such that m is less than or equal to a sub n over b sub n, which is less than or equal to big M, where n is greater than big N. And so m times b sub n is less than a sub n, which is less than big M times b sub n, when n is greater than big N. If the sum of b sub n converges, so does the sum of big M times b sub n. Thus, the sum of a sub n converges by part I of the comparison test if the sum of b sub n diverges, so does the sum of m times b sub n. And part 2 of the comparison test shows that the sum of a sub n diverges.